what is the relationship between the sample size and the sampling distribution of the sample means? So we continue with this example. Suppose that instead of 30, we have selected a sample of 100 applicants instead of the 30 originally considered. The expected value of the distribution of sample means continues to be mu regardless of the sample size, right? So in our example, the expected value continues to be 1697. Whenever the sample size is increased, then the standard error of the mean, this value, is decreased. With the increase of the sample size to n, the standard error of the mean is decreased to, how do we calculate that? Originally we took a sample size of 30 out of 900, which is less than 5%. But when we increase that value, the sample size at 100, then 100 divided by 900 is larger than 5%. So what that means is that we need to do the finite population correction factor. We're going to use it here, and we're going to use the standard error, the mean, there. Placing the values, this will be 900 minus 100 divided by 899. This sigma is the standard deviation of the population, square root of the sample size. This is the standard deviation of the distribution of sample means, where the sample is now of size 100. It's a smaller standard deviation. When the standard deviation is smaller, it means that the distribution is more concentrated around the mean, which continues to be mu. If we put that in pictures, it will be something like this. With sample size 30, this is the distribution of the sample means. With sample size 100, this is the distribution of the sample means. Notice that they are centered at the same value, but now this is more concentrated around the mean. We can ask the same question that we asked before. What is the probability we are between plus and minus the expected value? If we calculate that, n is equal 30, we know that this probability is equal to that. If now we use 100 and we repeat the process that we did, we are going to find out that now the probability is 0.7776. Because the sampling distribution with n equal 100 has a smaller standard error, then the values of the sample mean has less variability and tend to be closer to the population mean than the values with n equal 30. Okay? And that statement is just this. When the sample size is larger, then there is less variability, and the distribution of sample means tends to be more concentrated around the mean. And this is again graphically the same idea. The probability that we are now plus or minus 10 of the population mean, it will be 0.7776 for the sample size equal 100. Next, we are going to do estimations of the population proportion, sampling distribution of the sample proportions. And we're going to be making inference about the population proportions, and we're going to follow pretty much the same process that we did when we were estimating the sample mean. So we start with population proportion that we don't know. Okay, then we take a simple random sample with n elements out of the population. Okay, out of the sample, then we calculate the sample proportion. Okay, and then we use the sample proportion to make inference about the population proportion. And the ideas that we want to follow are parallel to the ideas that we used when we were doing inference for the population mean. The sampling distribution of the sample proportions is the probability distribution of all possible values of the sample proportion p bar. The expected value of the sample proportions has an expected value, and the expected value is equal to the population proportion. P bar is the sample proportion, and P is the population proportion, which means that the sample proportion is an unbiased estimate of the population proportion. How about the standard deviation of this distribution? The standard deviation of the sample proportions, we have two cases, as in the population mean. In the first case, we have an infinite population, and in that case, the standard deviation of the distribution of the sample proportions that we call the standard error of the proportion is calculated using this formula here. The population proportion times 1 minus the population proportion divided by n, and then the square root. Note that this is the population proportion that in most cases we don't know, we want to estimate. Okay, so the standard error of the proportion involves the proportion of the population that we want to estimate. In the finite case, we have the same expression as in the infinite population, and we have this correction factor here. The same applies if the relationship between lowercase n and uppercase n is that this is less than 5% of the big one, then we can assume that the population is infinite. And remember, this is the finite population correction factor. Now, the sampling distribution of the sample proportions can be approximated by a normal distribution whenever the sample size is large enough to satisfy the following conditions. The sample size times p, population proportion, is greater than or equal 5, and the sample size times 1 minus p is greater than or equal 5. As soon as we satisfy these two properties, then we can guarantee that the sample distribution of the sample proportions can be approximated by a normal distribution. When these conditions are satisfied, then the probability distribution of x in the sample proportion can be approximated by a normal distribution. Note that here we have p, right? P is a population parameter that in most cases we don't know and we want to estimate. With this information we can do an example, okay? And this builds up on the example that we have been working for this chapter about St. Andrews College. 72% of the prospective students applying to St. Andrews College desire on-campus housing. What is the probability that a simple random sample of 30 applicants will provide an estimate of the population proportion of applicants desiring on-campus housing that is within plus or minus 0.05 of the actual population proportion? This is the way we're going to proceed. Keep in mind these steps, because these are the steps that we're going to be following all the time. N is equal 30, P is equal 0.72 or 72%, and this is the population proportion that we know. In most cases we won't know this value and we will have to use an approximation of this value. But luckily, for this example, we know it. The normal distribution will be an acceptable approximation, because if we calculate n times p and n times 1 minus p, we get numbers that are both greater than or equal 5. Now I want to emphasize that both greater than or equal 5. If only one is greater than or equal 5 but the other is not, then we cannot use the normal distribution as an approximation. Okay, so both properties have to be satisfied. Both numbers have to be greater than or equal. We can guarantee that we are in this situation. The distribution of the sample proportions is going to be approximated by a normal distribution with mean or expected value 0.72 and a standard deviation calculated by the standard error of the proportion. So we replace the values 0.72, 1 minus 0.72 divided by the sample size, the square root, and we get the standard error of the proportion. Okay, so now we need to do some probability, right? We need to calculate probabilities, but this is going to be easy because this, we can assume, is a normal distribution. We proceed as usual. To calculate probabilities, we first calculate the z-score of the upper endpoint. The z-score is 0.61, right? And then we find the area under the curve to the left of the upper endpoint by looking at the standard normal table. We use the standard normal table to find out what is the area to the left of that z-score. Graphically, this is what we are doing. Then we repeat the same, but now for the lower end of the interval. Okay, and then we use the standard normal table to calculate the area to the left. And this is graphically what we are doing. And then the area in between, we just subtract the areas, 0.4582. Okay, so that's the probability. The estimate will be between 0.67 and 0.77. And graphically, this is what we did.